So, we usually do a lab for this, where we make three different types of solutions where you take a solute, and we generally use sodium acetate, some sort of ionic solid that's soluble in water, a polar solvent, and we dump it in there and you shake it and it dissolves. If it all dissolves, you've created what's known as an unsaturated solution, meaning you could put more in until it stops dissolving. So undissolved solution means you haven't maxed out how much is able to dissolve. So again, that's called unsaturated. Now, a saturated solution is when you've put so much solute in that it stops dissolving, and you will see the solid kind of collect at the bottom of the container, whether it's a beaker or a test tube or whatnot. Saturated is when you've maxed out how much solid can dissolve, and there remains undissolved solid. All right. Now, to make a solution super saturated, you can prepare it by usually forcing the solute to dissolve. So there's a couple ways to force solutes to dissolve in a solvent. Temperature, pressure, volume, and we're going to focus really today on temperature. So because we're going to talk about solid solutes dissolving and not like gases dissolving in solvent. So a supersaturated solution is prepared by saturating a solution and then putting even more solute in there that remains undissolved, and then forcing that solute to dissolve by heating it up. And the question is why can more solid dissolve when you heat the solution up? How come more solid dissolves when you heat the solution up? Well, when you dissolve more solid, the particles move faster. When they move faster, they can break apart easier. So if they break apart easier, they are more soluble. And then what happens is you can take that supersaturated solution and cool it back down to room temperature. Now, if you leave it undisturbed, you have a super duper 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 unstable supersaturated solution. A solution that at room temperature wouldn't have normally allowed all of that solute to be dissolved, but because you forced it to dissolve by heating it and then recooling it, you've created a supersaturated solution. So let's talk about the two processes. So if you take a solute and you dissolve it in a solvent, you form a solution. A solute and a solvent makes a solution. It's called dissolution or dissolving. Again, in the lab, we usually use sodium acetate, and we put it in water. And in the lab, I ask you to feel the test tube when we do this. So when you dissolve sodium acetate in water, it actually dissolves or dissociates endothermically. So how is the test tube going to feel if something dissolves endothermically? This is very important from the thermochem chapter. Cold. Very good. So the test tube feels cold. And now actually you can do this at home with normal table salt. If you get room temperature water and put it like in a small cup or something, and then you dump a bunch of salt in there, sodium chloride, salt specifically, because you probably don't have sodium acetate at home, and you stir it, you'll notice that the container will feel colder. A lot of salts dissolve endothermically. Now, not all of them, but a lot of them do. So not all dissolution processes are endothermic, but this specific one is, okay? So when we do this, we make the solution, right? And then we keep adding and adding and adding until the solute stops dissolving and you've created a saturated solution. And then when we do the lab, I have you keep adding more and more and more until you create like a really, really, really saturated solution. And then I ask you to heat it. And heating it allows you to force the solution to become super saturated, where all of the solute dissolves, and then you cool it back down to room temperature. Now, when you cool it back down to room temperature, the slightest disturbance, because it's super unstable being super saturated, meaning if you add just the tiniest little piece of sodium acetate to your test tube, the entire test tube will crystallize, all of your solute precipitates out of solution and comes back out because it is super saturated. It doesn't want to stay that way. Now, it's really important to create this crystallization and allow this to happen that you have to let it cool to room temperature. If you take and make a super saturated solution and it's hot, and then you drop another tiny little crystal in it, guess what the crystal's going to do? It's going to dissolve because the solution's still hot. It's unstable when it's back at room temperature. And again, these look like opposite processes. When you have the supersaturated solution, if you disturb it and the solute gets spit back out or precipitates out, this process is called crystallization. So dissolving is called dissolution. The solute precipitating out is called crystallization. And in fact, this is how we make the Christmas ornaments, is by preparing a supersaturated solution, putting your ornament in it, and then when it cools down to room temperature, the ornament itself is a disturbance to the solution, so the crystals form on it. It's really this exact process. So if the sodium acetate dissolves endothermically, guess how it crystallizes temperature-wise? If it dissolves endothermically, it crystallizes exothermically. These are opposite processes of each other, so they should have the opposite process of heat. And in fact, this process releases a lot of heat. In fact, when we do this, when we have done this in the past as a lab, sometimes the test tube gets so hot during the crystallization process that you can't even touch it. And it's not because the solution is hot, right? Remember, you cool it down to room temperature. It's because the process of crystallization in this example with sodium acetate is an exothermic process. Okay. So all solutes, which in this chart, we're looking at ionic, we're looking at different salts. Most solutes, the majority, and this is what I care about, increase their solubility the more you heat them up. So let's look at potassium nitrate. It's my potassium nitrate line. If you're on the line, you're at the saturated point. It's apparent that my solvent is water. So look at 10 degrees Celsius, I can get 20 grams of potassium nitrate to dissolve, and that's where I max out. However, if I heat it up to 20, I can get 30 grams of it to dissolve. So let's say you're at 20 degrees Celsius and you've only put in, you're at 20 degrees Celsius and you've only put in 10 grams of potassium nitrate. You're unsaturated. You can put more in all the way up into here. If you're at 20 degrees Celsius and you've only put in 20 grams, you can still put more in up to here. Okay, you're unsaturated. When you're on the line, you're saturated, and when you're above the line, for example, if you put in potassium nitrate and you put in, let's see how much I want to put in. 30 grams at 10 degrees Celsius. So I put in 30 grams at 10 degrees Celsius. I have too much, right? I'm only allowed to put 20 in. But if I heat it to 20 or a little bit past 20 temperatures down here, I can get it to dissolve. But that would mean when I cool it back down, that much will precipitate back out. And again, all different salts have slightly different solubilities. Cerium sulfate is one that is an exception to this, but I'm not going to be kind of concerned with that. Most salts or solutes, solid solutes, these are for solid solutes. As you heat them up, they become more soluble because they gain kinetic energy. They're able to break apart more. Breaking apart more means more soluble. Okay, so again, this is just a solubility chart of different ionic compounds in solution. This last part are about colloids, and again, I don't need you to know the in detail depths of this, but colloids are just particles that are kind of suspended. Think of them just like kind of, when something's suspended, just kind of like hanging out in solution. So they're bigger than like our ions, like our salt ions that break apart, or like our sugar molecules that break apart. They're bigger than that, but they're not big enough to have like gravity pull them down and sink to the bottom. So what they do, because they're not heavy enough, they're not big enough to like sink to the bottom and put a solid on the bottom, those particles kind of just sit there like floating around in solution, but they're bigger than like our ions floating around. Now, with our naked eye, because our eyes aren't actually that great, you might not be able to tell a colloidal solution just by looking at it. So colloidal solutions can often be determined by shining light on them. Okay, so if you look at these two containers, this would be some sort of normal solution like we're used to, like an aqueous solution, okay? And I realize it is colored, which doesn't matter, but it is considered transparent, meaning even though it's colored, it's like a clear looking color. It's transparent. You can see through it, okay? Now, before this light projector would be on, before you would turn it on, these two things would look identical, okay? To the naked eye, it is sometimes difficult to point out a colloidal solution. But the Tyndall effect means you shine light on it, and because the particles are actually bigger in a colloidal solution than, let's say, ions or molecules that have dissolved and maybe this is sugar water that's been dyed, or maybe it's salt water that's been dyed with red dye, okay? A colloidal solution to the naked eye might not look any different than an aqueous solution. However, because the particles are not big enough to sink to the bottom where you would see solid at the bottom, the particles are suspended in the solution so that they're big enough that when you shine light on them, though, the light scatters. So you can see that there are definitely bigger particles dissolved in this solution, this colloidal solution, as opposed to this like normal aqueous solution we're used to. Look, the light passes right through this first container, but it gets scattered by the second container because it's running into bigger particles that have the ability to scatter the light. And this is called the Tyndall effect. So a colloidal solution is just a different kind of solution with particles suspended that are bigger than any sort of ions or molecular solutes floating around in a normal aqueous solution that we're used to, like a sugar water or a salt water, okay? Now, the last thing I want to show you for this part of solutions is this really super duper cheesy but I think hilarious video all about solutions and a lot of everything that we've learned on this topic, this very short topic of solutions, with like polar, non-polar, and why things interact with one another. And there's something on here I do want to briefly mention that is no longer in the AP curriculum, and it's called freezing point depression and boiling point elevation. Those are called colligative properties, and they're no longer on the AP test. However, I do want to share with you what they're about because they are really important in a lot of aspects of everyday life. So freezing point depression is when you take and you put a solute in a solvent that causes the solvent to freeze at a lower temperature. That's what depression means. And then boiling point elevation is where you take a solvent and you put something in it, some sort of solute in it, that causes that substance to boil at higher temperatures, okay? So you go, well, why would you want to do this? Well, I don't know. Does anybody know an example in everyday life where you may have encountered freezing point depression or something that people might do for freezing point depression? Salt and ice, beautiful. So I always get that, salt and ice. And like, so what about salt and ice though? What do we know about salt and ice? So if you've ever made ice cream, you can't just use ice and like milk and sugar and vanilla or whatever, right? Because all you're going to get is just cold milk or cold ice cream, cold milky ice cream. So they usually use rock salt. Now, why is that? Because salt can lower the freezing point of water, so it can make it colder, okay? And if it can take it below 0 at room temperature, then you can get the milky milkshake-like thing to turn into more like ice cream. Where else do they use this concept of salt and ice or water? Definitely not here in Huntington Beach, but maybe like somewhere in like Minnesota, Alaska. Probably not Alaska, it's probably too cold there. Beautiful. Thanks, Micah. So they salt the roads, and you go, well, why would they do that? Well, they put salt on the roads because, when it snows there, snow is water, right? It can help the water from not freezing at 0, but freezing below 0. So water normally freezes at 0, right? But if you add salt to it, the salt interferes with the ability of water to hydrogen bond. And so because it gets in the way, it does not solidify as easy. So now instead of water freezing at 0, water doesn't freeze to like maybe -4, -5. Why is this helpful? Well, this is helpful, right? Because when it snows or freezes, the roads are really dangerous, right? Slippery ice. So now you've caused the roads to not freeze or be icy as easily. It can get colder without the roads freezing or turning icy, and that's good for safety reasons, right? Because it's very dangerous to drive on ice. And so they use this in places where it gets really cold like that and snows. How about your car? Antifreeze, right? When it gets really cold in those places, you put antifreeze to keep the liquids in your car from freezing, because then your car won't work properly. So again, this is that same concept. It's called freezing point depression. Now, the opposite of freezing point depression is obviously boiling point elevation, but it happens in the same way, where you take a solute, you put it in a solvent. Again, I'm going to use salt and water. It's just easiest to talk about. And the solute interferes with the ability of the substance to be able to boil. So it elevates its boiling point, making it harder to boil. So if you want to try this at home with like a thermometer, if you put a ton of salt in water and try to get it to boil, the water doesn't boil at 100. It actually boils at a higher number than 100. Now you have to be careful, because if you're using tap water has impurities in it, so that can affect your results. But again, that's called boiling point elevation, and these are colligative properties of solutions, which is what this whole chapter is about, that they've just seem to steer away from, which I'm not really a big fan of, but it's, it is what it is. But they are presented in this little awesome music video about solutions, so I just wanted to kind of share it with you, and so you weren't like super confused on what they were talking about, because again, this did used to be a pretty big part of the topic. And again, like coolant is used to keep your car cool, right? So it doesn't overheat. It's a boiling point elevator. It interferes with the solutions to keep anything from boiling at too hot of temperature. So if it gets really, really hot outside, things don't start boiling in your car, all your fluids in your car, and totally ruin your car. Again, the coolant is a boiling point elevator. It interferes with the ability of the substance to boil, making it harder to boil, which is good if it gets too hot. So again, these are pretty applicable in everyday life solution concepts, but again, they are not tested in here because they're not on the AP test. So I'm going to give you a second to watch my beautiful, cheesy, also hilarious video.
For those about to dissolve, we salute you.
Nice. Great. Now we're going to get sued by AC/DC.
Salt is something water in a beaker today. The ions broke apart in the usual way. The molecules of water kept the ions apart. A salt solution formed, but that's only the start. Homogeneous, same throughout. Homogeneous, same throughout. Solvents that are polar can dissolve solutes that are polar or ionic. That is really cute. Water and nonpolar solutes just won't mix, but a nonpolar solvent like benzene can fix. Like dissolves like polar and polar. Like dissolves like nonpolar and nonpolar. When all the solvent molecules used up and are stuck to the solute ions in your cup. Solution saturated, it is full for sure. Solubility's been reached for that temperature. Saturation on the line. Saturation on the line. If there's still some water molecules unstuck, then more solute can dissolve. Hey, you're in luck. Solution is unsaturated, can't you see? You haven't yet reached the solubility. Unsaturated. Put more in. Unsaturated. Put more in. If you put more solute in, then you be dissolved. Then a supersaturation situation's involved. The excess falls out as a precipitate, or the solution is unstable sodium acetate. Supersaturation. Precipitate. Supersaturation. Precipitate. A salt dissolved in water in a beaker today. The ice broke apart in the usual way. They made it harder for the water to boil and freeze, so the phase temperature gets a few degrees. Colligative properties depend on concentration. Colligative properties depend on concentration.
Electrolytes have a greater effect on the melting and boiling point of the solution than non-electrolytes.
More solute that's dissolved got more effect. Solution's boiling point increases direct. The freezing point decreases, which is really nice. In the winter, salt on roads can prevent the ice. Add a solute, boiling point goes up. Add a solute, freezing point goes down. That is wicked cool. Solutions rule.
So you are welcome for that amazing solutions video. Again, I thought that was a really good job of summing up the solutions topics we've been going over. But we do have one last thing we have to discuss about solutions that is going to roll over into our chemical kinetics topic, which is next topic. And that is going to be spectroscopy and Beer's law. And if you haven't been listening until now, this is something you really need to pay good attention on. This is super important stuff. I guarantee that this will be on the AP test. They seem to really, really like this topic. So let's go into what this is. So Beer-Lambert law, which is often referred to as Beer's law, is going to be an equation, which we'll get to in a little bit. But the whole idea, so remember spectroscopy, we have different types of spectroscopy. We have mass spectroscopy. That identifies like different isotopes. If you remember, we have photoelectric spectroscopy, PES. That was for like electron configuration and ionization energies, how tightly electrons were held to the nucleus of the atom. This spectroscopy is specifically used to determine concentration of colored analytes. Analytes are just like solutions that we're looking at, okay? Colored solutions, colored analytes, all right? And you go, well, how is this done? Well, this is done by shining a specific wavelength or color of light, okay, onto a colored solution and seeing how much of the light passes through and how much of the light that is absorbed. So if you look right here, this is some sort of color light being shown, a specific color. I don't know, let's say it's yellow, okay? And then there's usually a detector. So some of it will pass through and then some of it will be absorbed by the solution, depending on how concentrated the solution is. Now, this only works for colored solutions because if the solution is colorless, any color light will pass through. I don't care what color you shoot at it. Colorless solutions don't absorb any colors of light. That's why they're colorless, okay? They also don't reflect, but that's a whole nother thing. So anyways, so the intensity of the light is just the brightness of the light. Okay, so the brighter the light is, the more intense it is. Absorption and transmittance seem to be opposite of one another. So whatever light is absorbed, it's because it didn't get transmitted. Whatever light is transmitted, it's because it wasn't able to be absorbed. So these are just some words we're going to be using. All right, so in our lab, we do have these on campus. This is a spectrophotometer. This right here is like a little lid. You open it up to put your sample, and your sample is in like what's known as a cuvette, which is like a fancy test tube. And there's some things we'll talk more about the cuvette. Anyway, you shine a certain wavelength of light. So this dial right here, you get to pick all different colors of wavelength, whichever wavelength you pick, and we'll talk about how to pick which one. And then I know it's kind of hard to see, but there's a switch up here, like where you can switch between transmittance or absorbance. So you can either measure percent transmittance or you can measure absorbance. It doesn't matter which one, because remember, they're basically opposite of each other. So you shine this certain wavelength of light that breaks through the prism, and that color light is picked, right? So you have the light, the prism, you pick what color of the prism, and it blocks all of the rest of the colors. And then you have your sample, and then there's a detector that measures whatever you're wanting to detect, absorbance, and it reads it out for you, or percent transmittance, and it reads it out for you. So however much light is passing through or however much light is not passing through. okay, based on the intensity of the light. So that's how the machine works. It's called a spectrophotometer. Okay, so I'm going to use potassium permanganate as my example. Does anybody remember what color potassium permanganate is? It's purple. Nice. And it's not the potassium, it's the permanganate. MnO4 minus ions are purple in solution, okay? So I have 3 cuvettes or test tubes, okay? And I'm going to make 3 different solutions. Okay. How would you rank these on highest concentration to lowest concentration, kind of just based how I'm trying to just color, right? So 1, 2, 3. Is number 1 the highest or the lowest concentration? Lowest, okay. So this is like low concentration right here, and this would be high concentration right here, right? Relative. Okay, so if you go to shine light at this, and then we'll talk about what color later, but this is just the generic. You go to shine light at this, if there's not a lot of dissolved particles, so right, not a lot of dissolved particles means low concentration. Will more light get absorbed or will more light pass through if there's not a lot of concentration or dissolved particles? Well, way more light should be transmitted, right? If there's not a lot of dissolved particles, not a lot of light will get absorbed, right? It's almost like the more concentrated it is, that light being able to travel through gets blocked when it's more concentrated. When it's less concentrated, it can easily pass through, okay? The more concentrated it becomes, the less light that's transmitted, right? So you shine the light on it, but like some of it gets absorbed because there's more dissolved particles. So not as much is being able to be transmitted. And then even more concentrated, right? You shine the light on it and almost like it's stuck in there. Even less light will be able to pass through. So more absorption, less transmittance. Are there any questions on the difference between concentration and absorbance and transmittance before I move on? Okay. So now, because our solutions are colored, we have to be able to decide what the appropriate wavelength is to shine at our solution. So this is going to be a color concept that I don't expect you to memorize. I do expect you to know how to use the data though. So what they do is they take the sample. So let's say we have this sample. I'm going to say I don't know who it is yet, okay? Oops. They take the sample, whoever it is, and they shoot different wavelengths of light at it. So they shoot 400 at it, and then they plot the absorbance. And then they shoot 450 at it, and they plot the absorbance. And then maybe 470 and plot the absorbance. And then they change the wavelength to 500 and plot the absorbance. Never changing the sample. 550, plot the absorbance. 600, plot the absorbance, right? And they get this data. They shoot all different wavelengths of light, all different colors of light, and see which colors are being absorbed and which colors are not. And this is important because when you have a sample and you're trying to figure out what color light you're supposed to shoot at it, the most important color of light or wavelength or color of light is going to be the one that has the highest absorbance. And the question is, why? So when we see color, it is not because that color is being absorbed. It's because that color is being emitted. So like when we see something that's purple, it's absorbing all colors of the rainbow, but purple. Purple is being emitted. That's why we're seeing purple. So when we pick what color we want to use, so these are just different different ways to represent perceived and emitted and absorbed colors. So here's the color wheel. No, you don't have to memorize it. Yes, you have to know how to use it. So we just said what? Potassium permanganate, right? We said potassium permanganate is purple. It looks purple to us. So what does that mean? It means all of the other colors but purple are absorbed. So this, all of these colors are absorbed. But the thing is one of the colors will be the most absorbed, and that's the one we want to focus on. Does anybody know how to figure out who the most absorbed color is for something, for example, that's purple? So something like potassium permanganate looks purple to us. Which color of light is the most absorbed by violet? Yellow. Very good. It's always the one that's opposite to it. So things that look violet absorb yellow light the most. Now, it still absorbs orange and red and green and blue, but it absorbs yellow the most. So that would be the color light we would choose to shoot at our sample. So when we're back here, the color of light that we're wanting to use to shoot at our sample to determine concentration is going to be yellow light. Okay, so yellow light. And you go, well, why? Well, if you're trying to figure out concentration, you want to know, you want to shine light at it that is going to get absorbed by the solute. And so yellow light is the most absorbed. So the more purple that's in there, the more the yellow light can be absorbed. And the more the yellow light can be absorbed, when the yellow light is absorbed, we're going to have a mathematical way to determine concentration called Beer's law. So again, this is just another chart of different colors. So if something looks green, it's because it's absorbing all of the colors, but mostly red. If something looks violet, like potassium permanganate, it's absorbing all the colors other than violet, but mostly heavily yellow. And these are corresponding wavelengths, okay? So if I give you this same chart that we had to just kind of look, first question is, what is the best wavelength of light to shine at whoever this sample is? What is the optimum wavelength of light to shine at this sample? So pretty much you're finding the biggest peak. You want to find the color of light that is, or the wavelength of light that is the most absorbed. That'd be here, right? This is the highest peak. Sorry, I mean, this is like not the best straight line. Wow, best straight line, okay? But ish here, ugh, geez, whatever, you know what I mean. So this is 400, 450, 500. So I don't know, 470, 475-ish. That's the most absorbed light. So 475 nanometers has the highest absorption. This is the optimum color of light to shine at the sample. So let's go back to our color wheel. Where's 475? Blue. So we want to shine blue light at the sample, right? Which means what color is the sample most likely? If we want to shine blue light at it because it's the most absorbed. Which color absorbs the most blue light? Well, that's its opposite color, orange. So the sample is likely orange in color, okay? Now you go, okay, orange in color. So I know you don't probably know this, but solutions of dichromate are often orange in color, like sodium dichromate, lithium dichromate, potassium dichromate. So maybe it's a sodium dichromate solution that we're trying to find its concentration of using a spectrophotometer. Again, that's the name of the machine, okay? So again, the best wavelength is something like 470, 475. There would be a range that would be acceptable. And then what color is the analyte being tested? Well, the analyte being tested is likely orange if we're trying to shoot a wavelength at it of 475. Okay, You guys seem to be doing good so far, so let's keep going. So, practice MCQ. The student wants to run an experiment with the greatest sensitivity for A. So if you look on here, A is blue. So we're focusing on our dashed line, our blue dashed line. The data shown above, this should say below, was obtained for A and C, and they did a variety of different wavelengths. So they took these samples and they shone different wavelengths of light at them and measured absorbance at different spots and then plotted the data. What is the best wavelength to use for sensitivity to A? So here's your options. A, B, C, or D? What do you guys say? Great. D, look it. This has the most absorbance right here. Okay. So I know you don't have this memorized, but around this wavelength is the color red. So for sample A, they're using the color red red light to shoot at it. So they'd be shooting red light at this sample. And see how much red light passes through or how much gets absorbed. What's the opposite of red on the color wheel? Did you guys remember? Can you guys go look? It is green. So most likely this sample is green. And nickel 2 plus ions are a common sample that's green. Nickel, like nickel 2 chloride, nickel 2 nitrate, very common nickel 2 plus ions are a green sort of solution. Okay, for specifically substance A. Okay, great. Let's keep going. All right, let's talk about absorption versus concentration a little bit again. So I'm going to go back. Because the Beer-Lambert law is a direct relationship between absorption and concentration. And now we had said, okay, we're going to shine yellow light at it, and right, tons of yellow light will come out. Okay, so how does absorption and concentration relate? Well, this is low concentration, right? What kind of absorbance in this first test tube? High or low? So is a lot of light being passed through, or is a lot of light being absorbed? Well, a lot of light is passing through, right? Transmitted, so that's a low absorbance. Not a lot is being absorbed. This is a really high concentration, okay? And because it's so concentrated, not a lot of light is passing through, which means a lot of the light is being absorbed if it can't pass through. If it can't pass through, it's because the solution is stopping it from passing through. So this kind of relationship where when one thing goes down, the other thing goes down, or when one thing goes up, the other thing goes up, is called a direct proportion. It's a direct relationship mathematically. So Beer's law has an equation that represents that. And it's a linear law, and it's A equals ABC. So you should notice that A is on this side. So if C goes up, which is concentration, A goes up. Meaning if C goes down, A goes down. This is mathematically how that works, okay? Now, this is a linear relationship, so we're going to talk a little bit more about what this means in just a second. But again, A equals ABC is Beer's law. So if you go on your equation sheet and you go to the second page and you scroll down, you will see Beer's law. It is right here. Now, if you don't end up remembering on a test what these letters stand for, don't forget that you kind of have this legend over here that tells you what everything stands for. So let's go back. What does A stand for? A stands for absorbance, okay? This little baby A is called the molar absorptivity constant, and it's a constant specific to the who is in the solution. So like potassium permanganate would have an A absorptivity constant. but like copper 2 plus, which is blue in solution, would have a different absorptivity constant. And then like nickel 2 plus would have a different absorptivity constant. So it depends on who you're actually working with. What colored solution are you working with? Is it red? Is it blue? Is it green? And so they change based on that. Now, B is the path length, which is how wide the cuvette is. So I'm going to go back to what I mean by that. The distance that the light has to travel through the cuvette is your path length. So this is what B is. And they measure it with a ruler, okay? And the unit is centimeters, okay? So it's how the distance, the width, basically, of the cuvette. How far the light has to travel through the sample, which is why they call it the path length, okay? And now what's interesting is C is concentration. Now, until now, we've always had concentration represented by big capital M. Look at it. This is what we've always done concentration with. Big capital M. But for Beer's law alone, C is going to actually also represent concentration with the units of molarity, just like big capital M. A is unitless. Big capital A is unitless. So here's kind of how the units are. Little a's units are m minus 1 centimeters minus 1 times B is centimeters, right? Path length is centimeters. And then concentration is molarity. So guess what they all do? They cancel, okay? So that's what makes A unitless. Now, because I said this is a linear relationship, what that means is this is the equation of a straight line. So now we have to talk about what that means. So absorbance will be my y-axis or my y value. The AB term combined is my slope. A and B together is my slope. And then C is my concentration, which is my x-axis. Y equals mx. Now, if you would like to, you can call this plus 0, because if you are plotting absorbance versus concentration, y, x, right? If something has no concentration, it should have no absorbance, right? Because there's nothing in it, right? So that's why this is kind of like just not included in my equation, because it's 0. The y-intercept for absorbance versus concentration should always be 0, 0. If a solution is not concentrated, it should not absorb any color of light. There's no particles in it, dissolved in it, to absorb any light. Okay. We are going to do a practice problem. So, what is the concentration of a 1 centimeter sample? So this is path length. So meaning when you put it in the test tube, this distance of the test tube is 1 centimeter. That's B. Concentration in Beer's law is C. And I give you an absorbance, that's big capital A, and I give you that number. So how do I know, it says what is the concentration, how do I know that I don't use this equation? Molarity equals moles per liter, right? Because molarity is concentration. How do I know I'm not using this? Well, based on what they give you, I see A and absorbance. I don't see moles. I don't see liters. This is like not useful right now, okay? So the only other equation that we have concentration in that has absorbance also in it is this. All right. So you go, okay, let's focus. I want concentration, so I'll put that in red. I don't know this. That's what I'm trying to find. I do have absorbance, so this is good. I have this guy, that's good. And I also have B, so that's good. But I do not have A. That's a problem. I have to find A because I don't have it. So we're going to go back to this. So I'm just going to rearrange this, right? Actually, I lied. We said that this is the equation of a straight line where absorbance is your y value. This whole thing is your m. This is your x. And then there's no plus b because we assume it's 0 because no concentration is no absorbance. So y equals mx. So what does AB equal? A and B combined equal m. What does m mean? So yes, you have to know this for the AP test. What does m stand for? Slope. Ooh. So AB is your slope. So what is slope? Sorry to do this to you, but slope is y2 minus y1 over x2 minus x1. So you need to pick 2 data points based on that data table to find the slope, or you can't do this problem because you have 2 unknowns right now. You have A you don't know and you have C you don't know, and you just can't do that. So if you find the slope, you know AB. If you know B, which you do, then you'll know A. So I just picked the first 2 data points usually. It doesn't matter though. Remember, this is a linear relationship. So 0.41 minus, so don't forget that this is X and this is Y. Concentration is my X, absorbance is my Y. So Y2, Y1, X2, X1, right? Now, my y-axis is absorbance, so it doesn't have units. Trying to remember, is this 1.4? Yes. So AB, which is my slope, is 1.4. Question so far? Well, now I know this, right? What are the units for AB? So just be careful. AB combined, A is m minus 1 centimeter minus 1. That's A itself. B is centimeter. So AB combined together is m minus 1. Well, remember the AB is 1.4 and B was 1. AB. So it is AB is 1.4 because B was still just 1. So if you take now and rearrange Beer's law to solve for C, A over AB is C. This is just an algebraic manipulation. The absorbance was 0.6 in the problem, I'm pretty sure. Okay. And we just said AB was 1.4 m minus 1. And so you calculate that out. And you get about 0.43. Now, what are the units for concentration? Well, this is m minus 1 in the bottom. So it's molar, which makes sense for concentration, right? So let's go back and look at our graph. Does that fit in our graph? So an absorbance of 0.6 would have us fall somewhere in between these two guys, right? This is between 0.5 and 0.69. So we said absorbance of 0.6, and we said its concentration was approximately 0.43. perfect. It falls in between this guy. This seems to follow our trend. That is a way to kind of check your answer. So again, how do you find A or AB is you have to find the slope. There's no way around it if it's not given. The only other way you would do this is if they gave you the number for A. Let's try this with Google Sheets. So I had a little bit of a rough time with the Google Sheets last class because I did it originally on Excel. So let me give you this link. So you can kind of open your own little Google Sheets. And then you just go ahead and put in the data. So remember that 0.2, 0.3, 0.4, 0.5 is your X. So I'm just showing you an alternate way. This will be the way you do it when we do this lab. You'll use actual graphing. Okay, so here's your X axis. Here's your Y values. Now this is what I was having the issue with because usually this is how I do it in Excel, but for some reason it's doing it a little bit differently on here. So I'm going to try one more time. So you go to insert chart. See, I know it's plotting both, which is very strange to me because there should be an X and a Y axis. I'm going to do Excel because this bothers me. And I just have better luck with it. I'll have to figure out how the Google Sheets work so that it doesn't do this. So if you open up Excel and you put it in there, it's definitely a lot easier. If it'll open. All right, so here's the data. Okay, so you have this data right here. And if you highlight it, see, like, watch, you can highlight like this. This is the easiest. And you do insert. And then I picked the scatter plot right here. Scatter plot. I mean, this is exactly what it should do on the other one. So it formats this line, okay? You should notice it should trend towards 0, 0. Now, I didn't make it do that because that wasn't a point on their data. And then if you right-click it, you can add trend line, okay? Maybe I'm just better at this, I guess, better at this than Sheets. And then you can go down here once you add the trend line and you can display the R² value. The R² value is how close something is to a straight line. If it equals 1, you have a perfect linear straight line. The closer the R² value is to 1, the more linear the line is. And then you can also display the equation on the chart. Oops. I'm just trying to make the equation bigger. Why isn't it not letting me? Whatever. If you didn't notice, the equation is y equals 1.4x. What is 1.4? That is the slope. So A equals ABC, right? So the 1.4. So we did it using the data points. This way has done it by having like the Excel or the Google Sheets do it for you, which is really nice. So I'm just showing you a way that we will be doing it in a lab-based setting as opposed to in a test-based setting where you're probably not going to spend time on a test graphing this. You're going to do the slope using y2 minus y1 equals x2 minus x1, okay? So we are going to finish off with this FRQ. I should be able to finish. It says a student is instructed to determine the concentration of a solution of cobalt 2 chloride. Now, I don't know if you know this, but do you know what color cobalt 2 is? I think it's very easy to want to think that cobalt 2 is blue because, right, we always hear the word like cobalt blue, but it's actually like a pinkish red color, okay? And so they use a spectrometric or colorimetric, so spectrophotometer or colorimeter, that's a machine, all right? And the student is provided with a concentrated 0.1 molar solution, and they make a bunch of other solutions. So they take the concentrated and they prepare standard solutions, which are just solutions with known concentration, okay? And they make a bunch of different ones. So they make 0.02, 0.04, 0.06, 0.08, and then of course they have their standard, which is 0.1. Okay, we're skipping A. I'm asking you to just do B, C, D, E, F. Okay, it says the student takes the 0.1 molar solution, so the super concentrated one, and they put it in the machine, and then they observe, they shoot different colors of light at it. They shoot 400 at it, they measure its transmittance. They shoot 440 at it, they measure its transmittance, 480, all these like different points you see. And they measure the transmittance, and then they do it again, but for absorbance. You should notice that these things look like opposite graphs. This is like the inverse of this one, all right? This is your transmittance graph. This is your absorbance graph. So the question becomes, the first question on here, it says identify, sorry, it's kind of hard to see because my thing, it says identify the optimum wavelength for the analysis. So which wavelength of light are you going to pick to shoot at this species? So we did that based on the most light that is absorbed, right? What color light you think? Or I'm sorry, what wavelength? It doesn't ask for color, it asks for a wavelength. So I see 500s. This is definitely the peak, right? I think 500 would be acceptable. 510, 515, right? Definitely before 520, but after 480. This would be the best wavelength. These would be an optimum range of wavelengths of light, nanometers, to shoot at that. Now I'm going to go back real quick. What color is that? $500, $515, green. Does this make sense? It should, because I just told you what color was cobalt 2 plus in solution. Like a reddish color, right? So this should make sense conceptually. Okay, so we did part B. That was part B. There would be an acceptable range on this FRQ. So then what the student does is the student takes and puts in a bunch of different samples. So let me discuss how this happens. They take a cuvette, which is just like a fancy test tube. They shine the green light at it. And this is like the 0.2 molar, okay? Or 0.02, excuse me. 0.020 molar. They shine the green light at it, 0.020, and it looks like the first reading is like 0.1, right? This is absorbance now and concentration. 0.12-ish absorbance. Okay, then they take it out and they put another sample in there, a different concentrated one. So like, let's say the let's do the 0.1 molar. I mean, they do, oh, no, actually, let's just do the 0.04 molar. So this is the 0.04 molar. Okay. Now, 0.04 molar should be more concentrated, right? Okay. And then they shoot green light at it. And then they measure the absorbance. And based on 0.4, it looks like it's 0.21, whatever. Okay. And then they take it out. And then they do it again with this sample. And then they take it out. And then they do it again with this sample, record, take it out. And they do it again with the most concentrated sample and record and take it out. And then they plot the data and they get this linear relationship because concentration and absorbance is linear. The more concentrated a solution, the more light is absorbed by the solution, the less the light can pass through, okay? So part C says the absorbance of an unknown solution is 0.275, and it's an unknown solution of the cobalt 2 chloride, okay? It's not just a random solution. We're still using the same solution. And so they put a random concentrated one in there, and they measure its absorbance, and they say its absorbance is 0.275. And they say, what is the concentration? Well, let's talk. The relationship between absorbance and concentration is this. We know A, because they measured it. We want to know C, and we're severely lacking AB. In fact, we don't even have B this time, but it shouldn't matter, because what does AB equal in a linear relationship? Y equals mx. And what's m? Slope, right? AB. So you need to pick two data points to find the slope. I am going to choose the last and the first. I'm going to pick this one and this one. You can pick any 2 points you want. Maybe the number comes out slightly different. The whole point is it doesn't matter. Okay? So this point and this point to get the slope. So this looks like 0.55 for my y2. So remember, slope is y2 minus y1 over x2 minus x1. So 0.55 minus, what's my y1? So this looks like 0.12-ish. Over. So this is x2, this is x1, so x2 is 0.1, and then this is where I went horribly wrong in my third period. So this is 0.1 minus, please notice, and this is what I went way too fast, this is not the y-intercept. And what I mean by that is, this point, if you look at it, is not being described as 0, 0. And I made that assumption, and it's not. This is 0.1 and 0.02. They have not shown you 0, 0. They have not like extrapolated the data backwards to show you that point. So the x is 0.02. Be very careful. I did that, and it messed me up so bad in class. So oops. So what is my slope? And again, if you use different data points, it'll come out slightly different, but we just need an approximate, okay? It looks like 5.375 if you'll use this exact data. So this is A equals 5.375 m minus 1, that's what AB is because it's slope, times C. Well, we know A, right? A is 0.275. So we'll divide both sides by 5.375 m minus 1, and you end up with C. So 0.275 divided by 5.375 is approximately, so concentration is approximately 0.051 molar, approximately, okay? So at an absorbance of 0.275, we have a molarity of 0.051. So let's talk about what that means. Look at the graph and make sure it makes sense. Where is 0.275 on this graph? Well, this is 0.2, absorbance. This is 0.25, so 0.275 is like right here-ish, right-ish. So if you go across about what concentration does that work out to be? I know I'm not very good at straight lines. I mean, this is pretty close to 0.05, right? So what we're saying is our calculation does make sense based on the data given in the graph. Okay. So that was C. I'm going to skip D just real quickly. Oh, Beer's Beer's law is an expression that includes 3 factors that determines the amount of light that passes through a solution. Identify 2 of these factors. So what's one? The concentration, right? The concentration of the solution will determine how much light passes through. How about the path length too? The wider or narrower the test tube will also determine how much light passes through. So the path length would be another one, okay? Part E says the student handles the sample container and holds it with their fingers and leaves fingerprints on it. How will it affect the calculated concentration of the unknown? So instead of talking, so A equals A, B, C. If you leave fingerprints on a test tube, will more or less light get absorbed? Actually, let's look at it this way. If you put fingerprints on the test tube, less light will be able to pass through, okay? Which means more light will be assumed to be absorbed, even though it's actually not, because it's just not having the ability to pass through because your fingerprints block it from being able to be passed through. So it will be an artificially high assumption that more light is being absorbed. Well, if more light is being absorbed, you're going to assume your concentration is higher. So you will have an artificially high concentration because of the fingerprints, because less light will be able to pass through. And it's not because of the solution, it's because your greasy paws got in the way of the light being able to make it through the test tube. And so you'll think that your solution must be more concentrated when really that might not be the case. Okay? So last thing, why is this method of determining the concentration of cobalt-2 chloride appropriate, whereas what we're doing right now, shining light through a solution, would not work for sodium chloride? This is a very important point, and then we are finished. Why is Beer's law in a spectrophotometer where we shoot red, orange, yellow, green, blue, indigo, violet light at a colored solution, why is that a great way to determine concentration of cobalt-2 chloride, but would be ineffective for something like salt water? Beautiful. Salt is colorless when it dissolves in solution. So to find concentration of a saltwater solution, this would not be an appropriate method because no matter what color light you shine on it, it's all going to pass through. You need to have colored solutions for this process, this Beer's law and this spectrophotometry to work. So the solution has to be colored for Beer's law or it won't work. Woo! We are finished. How are we doing?